Hey there, Sci2 kiddos. I'm going to use these slides to review the third gas law, Gay-Lussac's law. Again, let's just make sure we're feeling good about the previous two. Boyle's law was looking at the relationship between pressure and volume. They are inversely proportional, meaning they will always do the opposite of each other. Charles' law was looking at volume of a gas and temperature of a gas and found that they are directly proportional. If you increase one, you increase the other. Temperature, remember, must always be in Kelvin. The third law we're going to look at is Gay-Lussac's law. He was looking at the relationship between pressure and temperature and found that they are also directly proportional. Pressure is directly proportional to temperature. In other words, if you increase the temperature, you're going to increase the pressure. Or if you decrease the pressure, you're going to decrease the temperature, and so on. Again, we're assuming volume is constant and number of moles, or the amount of gas. So notice there's no V here. We're going to assume that volume stays the same throughout. Again, you don't have to memorize. I will provide it to you, but here's the equation. P1 over T1 is equal to P2 over T2. Just like before, pressure units can vary as long as they match. As long as P1 is the same as P2, that's fine. But temperature must be in Kelvin. Again, you cannot use degrees Celsius. You cannot use degrees Fahrenheit. It must be in Kelvin. I'll do this first example problem, and then you can try the second one. A container of a gas is initially at 0.500 atmospheres. That's my P1. At 25 degrees Celsius, that's my T1. But again, I got to add 273 to get the proper, it's going to be about 298 Kelvin. What will the pressure be at 125 degrees Celsius? So that's my T2. And again, got to do plus 273. And I'll find that my T2 is 398. Nice coincidence there in terms of the numbers being very similar. So this is, again, somewhere you're going to have to keep careful track. So again, remember the equation is P1 over T1 is equal to P2 over T2. P1 over T1 equals P2 over T2. So to set that up, we know that it's going to be 0.500 atmospheres of pressure divided by 298 Kelvin. Again, note we're not using degrees Celsius, you always use Kelvin. It's equal to our unknown P2 divided by 398 Kelvin. As I mentioned before, you just got to cross multiply to solve, okay? So we're going to rewrite this as 298 Kelvin times our unknown P2. Again, notice I cross multiplied here, is equal to 0.500. That's our atmospheres times 398. That's cross multiplying here. Divide both sides by 298 Kelvin. Those will cancel out. And over here, you're just doing 0.500 times 398 divided by 298. And notice, I didn't have the units here, but kelvins will cancel out, and you're left with atmospheres, which is what pressure is measured in. And again, remember, it's a directly proportional relationship. The temperature has increased, so we should expect the pressure to increase. You should get a P2 of about 0.668 atmospheres, which is indeed higher than 0.500. So the answer makes sense there. Okay, go ahead and try this second example, following a similar framework. Once again, don't forget to convert your temperature degrees Celsius into Kelvin. Let's always work with Kelvin. Okay, here's the answer that you should have gotten. You're trying to find the secondary pressure. It's unknown. What you should have gotten is about 182 millimeters of mercury. You can see how it's calculated here. In the real world, if you've ever used an aerosol can before, especially like that air cleaner that you can use to like clean your keyboard and things like that, you might notice that when you spray on an aerosol can, that spray is actually very, very cold. And that's because inside the container, these sprays are basically a liquid held at an incredibly high pressure. This is why you should never throw a aerosol can onto a fire, because there's just so much pressure inside them that could potentially explode. So lots of pressure on the inside, but when it's sprayed out, that pressure decreases. And again, they're directly proportional, therefore the temperature also decreases. And so that spray is actually very, very cold to the touch, especially if you've been using it for a while. Okay, hope that was helpful. Thanks.